All right, in this video, we're going to finish off what we didn't get to today and talk about inhibitors. Now, an inhibitor is something that will bind to an enzyme and either slow it down or stop it completely. So if an inhibitor will bind to an enzyme and never come off again, it's actually called an inactivator. However, if it binds to the enzyme and then can be removed, we call it an inhibitor. And based on how the inhibitor works, we give it different names. So we start with our competitive inhibitor. And a competitive inhibitor binds at the same exact location in the enzyme as our substrate. And since we're binding in the same location, they usually look the same as our substrate. For example, succinate works with the enzyme succinate dehydrogenase. A competitive inhibitor for this enzyme would be malonate because they look similar. They're only missing one carbon, but when malonate binds in the active site, the enzyme no longer works. A good competitive inhibitor are also transition state analogs, because remember, the enzyme really wants to lower the activation energy of the transition state. And so if your inhibitor looks like the transition state, your enzyme is likely to bind that and then stop working. Now let's look at the kinetics of a competitive inhibitor. And we have a new term to introduce, that's Ki, the inhibition constant. This is similar to Kas for acid, if you remember back from general chemistry and organic chemistry. And for a reaction that actually I have down here, enzyme plus substrate, or enzyme plus inhibitor makes my enzyme inhibitor complex. Ki is concentration of enzyme times inhibitor divided by complex. So the smaller Ki is, the better the binding. So if you see a Ki that's like times 10 to the minus 9, that's a very good inhibitor because it's going to bind to the enzyme a lot. Now, our Michaelis-Menten kinetics change a little bit with inhibitors. So if we look at our Michaelis-Menten equation right here, the difference is that we add this alpha term to Km, where alpha is equal to 1 plus inhibitor concentration divided by Ki. And what this means is that an competitive inhibitor raises the Km for an enzyme. So remember, Km is the substrate concentration where you go half your Vmax. Well, if we're increasing Km, that means it's harder to go 1/2 your maximum speed. It's harder to go your maximum speed. However, Vmax and turnover number are unchanged because you are competing. So if you have a lot of substrate, you can outcompete your inhibitor, bind normally, go to your Vmax normally. So that's a competitive inhibitor. And what happens when we do a Lineweaver-Burke for competitive inhibitor, what we'll see for different lines, here we have 3 lines. This is the same protein. One, you do an experiment without inhibitor, and then the blue and purple lines, you have inhibitor. More inhibitor in purple than in blue. And what you should see is since Vmax doesn't change, all the lines will cross the same point on the y-intercept. However, Km does change, and the stronger inhibitor, the closer Km gets to 0, or closer the x-intercept gets to 0 rather. Because remember, Km increases. This is a reciprocal plot. So if Km is increasing, that means 1/Km, which we are finding here, is decreasing. Hence, it's moving to 0 with more inhibitor. The next type of inhibitor we're going to look at is called uncompetitive. And what an uncompetitive does is that it'll bind the active site, so your reaction can no longer be complete. As shown here on the diagram for the equation, we have our uncompetitive binding to the ES complex. And so you get enzyme, substrate, and inhibitor all bound at the same time, which means the inhibitor does not bind to the active site, and then you get no reaction. Again, we have alphas. For uncompetitive, we use alpha prime. And both Vmax and Km are being lowered here. So both Vmax and Km are being lowered. So what does that mean on a Lineweaver-Burke? So on a Lineweaver-Burke, we get parallel lines. As we increase inhibitor, Vmax will get smaller, smaller, smaller. So it will go higher on the reciprocal. Km also gets smaller. And so parallel lines, uncompetitive. And the last type of inhibitor we're going to look at is mixed. And mixed is a little bit weird in that it behaves both like a competitive and uncompetitive. You also see this as non-competitive. And we can see this down here. We're binding to the free enzyme like competitive, and we can also bind to the enzyme substrate complex, just like uncompetitive. What this means is that Km, depending on which one is favored more, can either increase, decrease, or actually stay the same. So each enzyme will be different in that way. Vmax will decrease though. So Vmax is decreasing always in that. So what this means is that you'll never cross on the y-intercept. You'll always cross your lines somewhere here. Either you're going to have the same Km and they all meet at this one point, or they have different Kms as well, and so they'll cross at a different point. So that's mixed. So the take home really is I want you to understand how to differentiate these on a Lineweaver-Burke, understand what we're binding to and where. So free enzyme, enzyme substrate complex, active site, non-active site, and understand how Km and Vmax change. That's what we need to know for our 3 different types of enzymes. There's calculations to go with this, but we can skip calculations. This table is just showing how everything's affected, but really just know what I said on the last slide. Here's a good question for your understanding. And I'll just explain it, not answer it here. I'll put the answer up online, but I do want you to try this. So line A. Line A is an uninhibited enzyme plus substrate. I want to know of the 5 lines, B, C, D, E, and F, which one is acting as a competitive inhibitor to line A? Which one is acting a non-competitive inhibitor to line A? Which one's acting as an uncompetitive inhibitor to line A? So answer that and check back. Probably on Monday, I'll put the answers up. But with that, that is all the lecture material we have for this semester. So thanks for watching this video. If you have questions for the final exam, please put them on Blackboard. Otherwise, I hope to see you Monday. And if you're watching this after Monday, good luck on your final. Take care.